Welcome to Chemistry with Dr. Z. I'm Dr. Z, and in this video, I'm going to talk about simple and giant covalent structures. So let's start off by talking about simple covalent structures. So substances containing covalent bonds usually have simple molecular structures. So there are few atoms linked together by covalent bonds, so they have what we call simple molecular structure. Examples of these we can find like the simple molecules like carbon dioxide, like water, oxygen, and so on. They are all simple covalent compounds. The atoms within the molecules are held together by strong covalent bonds. So there are strong covalent bonds between the atoms within the molecules. However, the force of attraction between the different molecules are very weak. So there are very weak intermolecular forces between molecules. So we can see here in the example on the right, we have the two oxygen molecules with strong covalent bond between the atoms of each molecule symbol covalent 1, but the interaction or the forces of attraction between the molecules is very weak. So very weak intermolecular forces. Here on the left, we can find carbon dioxide, carbon with two oxygens with double bond or two covalent bond between each carbon and oxygen. And there is also a weak intermolecular forces between the molecules, but there is a strong covalent bond between the atoms within the molecules. So if the intermolecular forces or the forces of attraction between the molecules are weak, that means that they only need little energy, or they don't need strong energy or high energy to break these bonds, so they can melt and boil at low temperature. The melting and boiling points of simple covalent structures is quite low when we compare them to ionic structures. So most of these compounds you can find them as gases or as liquids at room temperature. Like here, these two examples, oxygen and carbon dioxide, they are both gases. Something like water, water as well is one of the simple covalent structures, but they exist as liquids, not as gases. So they still have low boiling points when we compare them to ionic structure, which are always exist as solids, and they have high melting and boiling points. If the size of the molecule increases, number of atoms within the molecule increase, then the intermolecular forces between the molecules as well will increase. That means the boiling and melting point of the molecule will increase. So increasing the size, increasing means increase in the intermolecular forces. That means increase in the boiling and melting points. One of the properties of the covalent compounds as well is that they do not conduct electricity, and this is expected because there are no charged ions or electrons that can carry electrical charge, so they do not conduct electricity. One of the examples of simple molecular structures is the polymer. So polymers are a long chain of repeated units. So like you have repeated unit, and this is a certain chemical unit, certain atoms arranged together, and then they are linked together like this. Repeated, the unit is keeps repeating itself, and they are linked together by covalent bonds. The polymers, as you can see, in polymers, they're gonna have a big structure. So they are big in structure, which means the intermolecular forces between the molecule is very big. The intermolecular forces between the molecules is much higher than the simple small molecular structures. So the melting and boiling points for these are quite high compared to the very small molecules. However, they are still lower than the melting and boiling points of the ionic compounds, because the intermolecular forces between covalent compounds is weaker than the intermolecular the electrostatic interaction between the ions in the giant ionic lattice. How can we draw the polymer? So we have a polymer here that we can see, which is the polyethylene. Polyethylene is one of the polymers that you're gonna study in the organic chemistry section. It's formed by repeating units of ethene. An ethene molecule is this molecule which has two carbon atoms. Each carbon atom is connected with two hydrogen atoms. So this is the repeating unit. So we cannot keep writing or drawing this unit. So instead of keep drawing this like drawing like that and so on both sides. So to simplify and to make it easier to draw the polymer, we only draw one of the repeated units, as you can see, and we put it between brackets and put the letter N, which refers to the number of repeated units. Because we don't know how many repeated units there are, so we simply put the repeating unit and then we put N between brackets. And don't forget to represent the covalent bond here. So that means that these carbons are connected to the same repeating units outside this bracket. What about the giant covalent structure? So giant covalent structure, in this type of structure, all the atoms are bonded to each other by strong covalent bonds. So instead of having certain molecules like the simple covalent structures with intermolecular forces in between them, all the atoms in the structure are bonded together by strong covalent bond. That means that in order to melt this structure or in order to melt this compound or that structure, we will call it structure rather than compound. In order to melt it, then you would need very high temperature in order to overcome the very strong covalent bonding between the atoms. Some of these examples can be seen here. So we have diamond. So diamond is one of the giant structure which has only carbon atoms. Each carbon atom is bonded with four other carbon atoms. So each one has four covalent bonds, as you can see here, and so on. So every carbon atom has four different atoms. We cannot draw all the atoms, otherwise the structure will be very big, but each carbon atom is bonded with four other carbon atoms, making four covalent bonds. There are no electrons, free electrons, no ions, so the diamond does not conduct electricity. The structure a diamond is very strong, and the melting point of diamond is very high. Another example we can see is graphite. So graphite is also another type of the giant covalent structure. It's different from the diamond. It's only formed from carbon as well. And the difference here is that each carbon atom is only bonded with three other carbon atoms. So it makes only three covalent bonds. There, we know that carbon has four electrons in its outer shell, so it shares only three electrons with other three carbons to make three covalent bonds, and there will be one electron that will be free, and because we have one free electron, then graphite can conduct electricity. So graphite is one of the exceptions of the covalent structure that can conduct electricity due to the presence of the free electron. The graphite will form sheets, as we can see here. Each sheet is formed of hexagonal carbon structures, and these sheets are linked together with weak bonds or weak intermolecular forces. So the sheets can slide across each other. They are not as strong, but still they have high melting points as well due to the massive number of covalent bonds that we need to break. A third example is silicon dioxide. Silicon dioxide is also called silica, and this is what sand is made of. So silicon dioxide is simply sand. So one grain of sand is formed of silica and oxygen, which are linked together with covalent bond. Again, we know that sand would have massive melting point. So this is because of the covalent bonding that you need to overcome in order to melt it. And it doesn't conduct electricity because there is no free electrons to conduct electricity or to carry the electrical charge.